So the question here is, could you analyze the stresses in a pressurized thin-walled cylindrical tank by Mohr circle? First, let's define the state of stress that we have in a pressurized thin-walled cylindrical tank like shown in this picture. This is a thin-walled cylinder kept in the axial direction in order to hold the pressure in. Let's call the internal pressure as P, wall thickness as little t, and the radius as r. Since the wall thickness is so small, we can neglect the differences in the radius between the inner and the outer circles. If I take a three-dimensional differential element in the r, theta, z coordinate system and look at the stresses, this is what we will see. There is a normal stress sigma 1 in the hoop direction. There is a normal stress sigma 2 in the axial direction. That's it. There are no other stresses. These other pictures collectively give you illustration of the meaning of these stresses. In terms of magnitude, you might recall the sigma 1 is given by this equation, PR over T. Sigma 2 is half of that, PR over 2T. So if I call this as sigma 0, this would be 2 times sigma 0, right? Once again, you can see that we could simplify this into a two-dimensional state of stress, like shown in this picture here. Instead of using the cylindrical coordinate system, we'll just simply call this as the XY coordinate system. Of course, in the radial direction, there is a normal stress in the inner surface, but not on the outer surface. For the purpose of the analysis here, we'll just focus on the theta z plane, which is this. Let's analyze the state of stress using the Mohr circle. The first step is to sketch the Mohr circle, and here is the sign convention we will use. Tensile normal stress is positive, clockwise shear stress is positive. So within this sign convention, here are the coordinates for the x and y planes, and here is the sketch of the Mohr circle. First, we make the observation that x and y planes are the principal planes, right? Planes with zero shear stresses are the principal planes, and therefore we don't even need to do the Mohr circle analysis to confirm that. The major principal stress is 2 sigma 0 and the minor principal stress is sigma 0. Both of these are tensile stresses. Now we come to the maximum shear stresses. Now just because we don't see any shear stresses on these planes, well, it doesn't mean there are no shear stresses on planes that are inclined at different angles, right? And because the circle has a non-zero radius, we can see there are planes with shear stresses. So these are the 2 points where we see the maximum shear stress. As is always the case, the magnitude of the maximum shear stress is the radius of the circle. So in other words, tau max is plus or minus r, and here we see the radius of the circle is this minus that divided by 2, right? So that will be sigma 0 over 2, and therefore tau max is plus or minus sigma 0 over 2. While there are multiple ways to find the direction, this is what I did over here. I took this radius, the radius that points to the x-plane, and rotated it counterclockwise through an angle of 90 degrees to get to this point. So the point containing the maximum shear stress. What I need to do in the xy plane is to take the x-axis and rotate that in the same sense, which is counterclockwise through an angle which is half of this angle right here, right? So it'll be 45 degrees to get to the plane where this shear stress is acting. And therefore this is that plane, the plane perpendicular to this line right there. Since the shear stress is a positive quantity on this plane, it is acting in the clockwise direction on that plane. The normal stress on that plane is the average between this and this, right? In other words, sigma average, which is 2 sigma 0 plus sigma 0 divided by 2, or 1.5 sigma 0. And of course, the magnitude of the shear stress is sigma 0 by 2. The plane perpendicular to that is the plane representing this point, where the shear stress has the same magnitude r, but the sign is negative, and therefore the direction of the shear stress on that plane is counterclockwise. The normal stress, of course, is the same, which is 1.5 sigma 0. And these are tensile normal stresses.